Well, hello and welcome again to our journey into complex analysis, and we're up to section 7 on Cauchy Integral Formula. So the following remarkable formula in fact enables us to deal with a much wider range of integrals, and it's probably the second most important in complex analysis theory. We begin with a simple lemma that we take any complex number z0, and we're going to look at the integral of 1 over z minus z0 inside this disk on this circle of centre z0 radius r. So where the picture's looking like this, we've got some circle here, make it look like a circle, so centre z0 and radius r, and the value of this integral turns out to be just 2 pi I. In fact, this factor 2 pi I we're going to see over and over again. It's one of those very ubiquitous numbers in complex analysis. And the proof of this is very easy. We just parameterize the circle in the usual way as z0 plus r e to the I theta for theta between 0 and 2 pi. Now when we substitute this in, this is going to give me the integral 0 to 2 pi. The dz is just going to give me r e to the I theta, I e to the I theta, and then z minus z0 is r e to the I theta. These cancel out. I just get an I, and you integrate, you get 2 pi I. Now, from that we can prove now this more general result, the so-called Cauchy Integral Formula, which I'll call CIF from now on. And here we take any analytic function which is analytic inside and on a simple closed path C. So the picture this time is here we have any closed path C, and we take Z0 to be an interior point. So there's the Z0. And the theorem says that if you integrate, so you want this f of z has to be analytic inside and on the contour, and if we integrate this function divided by z minus z0, then we get 2 pi I times f of z0. That is, we just substitute the z0 up into the numerator, multiply by 2 pi I, and there's the integral. So this is rather interesting because it's telling us the value of the function at an interior point in terms of an integral around the boundary. Now, as we've seen before, without penalty we could replace this contour C, which might be quite complicated, by just a small circle of radius delta. So we're going to put a little circle around this of radius delta. So this is my C delta here. And then the integral around C, since the function's analytic inside C, it's going to be analytic in between these two contours, and so I can just shrink the contour down to C delta. We've seen that idea before. And now I'm just going to substitute in Z is Z0 is parameterized, delta e to the I theta, where again theta goes 0 to 2 pi. You do that, well then you get the integral 0 to 2 pi. You get z minus z0, which is delta e to the I theta. You get f of z0 plus delta e to the I theta. And the dz, as we saw before, is I delta e to the I theta. And those terms, everything cancels out. We get an I at the beginning, and we just get f of z0 plus delta e to the I theta. Well, finally, if we now let delta become as small as we like, then this simply becomes, then this thing here just becomes f of z0, which is a constant, times I, and we integrate, we pick up the 2 pi, and there's the desired result. Now it's a fairly simple proof, but it's a very powerful fact here. Just to work through a couple of examples of how to use this. So we're going to look at the integral of e to the 2z on z minus 1 on around mod z equals 3, and then e to the 2z on z squared minus 4 mod z equals 3. So just do two worked examples of that. So here is the first one here. We've got, it's very simple. there's the integral, e to the 2z on z minus 1 around mod z equals 3. Always draw the picture. Make sure you mark in your z0, make sure it's in the contour, because of course if that point was outside the contour, the integral is 0 by Cauchy's theorem, but this is an interior point. So Cauchy integral formula says you just plug the number 1 up into the top, you get e squared, multiplied by 2 pi I. That's it, that's the value of the integral. No integration to be done, it just comes out immediately. For the second one, we have 2 points inside the contour. We've got one at 2 and one at minus 2, which make the denominator 0 here. So there are two ways of proceeding with this. One, which is the one I sort of prefer, is to replace our contour C. This function here, by the way, is analytic everywhere, as was the one up here, which I should have mentioned. So this function's analytic everywhere, so I'm going to replace the contour C by two little subcontours, gamma 1, gamma 2, that isolate these two singularities at plus or minus 2. So what I can do then is I can now replace this integral. I can split this up into the sum of two integrals, one around gamma 1 and one around gamma 2. And what I'm going to do is the one around gamma 1, that contains the singularity minus 2. So I'm going to factor z squared minus 4, leave the z plus 2 in the denominator and pull the z minus 2 up the top. And I get this function now, e to the 2z on z minus 2, but that's analytic inside gamma 1. And then I have the second integral around gamma 2, so this time I leave the z minus 2 down the bottom because 2 is now an interior point of this contour. And I pull the z plus 2 up the top, and I'll call that one f2. Now I can just apply Cauchy's integral formula to each of these. So I have 2 pi I times the first one I shove minus 2 up into the top, the second one I put plus 2 up into the top. Just evaluate those, this comes out. And we can take a bit of the 2 in here, we can combine these together, and we get I pi shine 4 after some simplification. The other method you can use is you could factor this as z squared minus 4 into z minus 2z plus 2. You could then use partial fractions on that and split that up into 1/4, 1 on z minus 2, minus 1/4, 1 on z plus 2 using partial fractions. And then you just apply Cauchy integral formula to the top and bottom, to each of these integrals, and again we get the same answer after we've simplified it. So there are a couple of little examples there. Now Cauchy's integral formula generalizes very nicely. So we get a generalized form of the Cauchy integral formula, and I'm just going to write this in this form now. Instead of using Z0, I'm just going to call it W here. W, of course, in the Cauchy integral formula is a constant, but one is then tempted to sort of formally differentiate this, but with respect to W, thinking of W now as some sort of parameter, and differentiate it formally with respect to that, just to see what happens. You can't really do that. I'm being very naughty in doing that, but let's just see what happens symbolically if we do that. So if I differentiate both sides with respect to W, then you get this. And that's very interesting. And then if you do it again, in fact you do it several times, you can come up with the following formula, which looks to be true, that this says that the nth derivative of f at W is n factorial on 2 pi I, and we get the power on the bottom becomes n plus 1. Now this last formula here, it's not proved the way I've done it, that's of course incorrect, but the last formula is called the Generalized Cauchy Integral Formula, and it's also got some remarkable consequences. Now a proper proof of this can be found in textbooks, so I'm not going to go through the proof of it here. This is just a fudge proof to show you that at least symbolically it makes sense, but to give a proper proof, a formal proof, you can have a look in the Churchill and Brown textbook. So as a simple example of that, we have a look at we're going to integrate sine of 2x on z to the 8th around z equal 1, and here's the worked solution for that. So here is the question, and again we should draw our little picture. Always draw the pictures of these things. So mod z equals 1, and there's 0 in the middle. So there's the interior point 0. So generalized Cauchy integral formula says, well, this is f of z, that's analytic everywhere. We've got z minus 0 to the 8, so the n in the formula is 7. So the answer is going to be 2 pi on 7 factorial, and I've got to get the 7th derivative of sine of 2z. Well, that's fairly easy. You're going to have to pull 2 out 7 times. You'll get 2 to the 7. And after you've done it 6 times, you get back to where you start from. 3, 4, no, you get minus where you start from. The 7th time is going to give you a cos, so you get minus cos 2z. Now you put z as 0 in, cos of 0 is 1, and I just end up with this expression here, 2 to the 8th, minus 2 to the 8th I pi on 7 factorial. So you can do lots more different sorts of integrals using Cauchy integral formula and the generalized version of that. Now, as I mentioned, there's a little challenge problem to have a look at if you want to play around with this a little bit. So here's the challenge problem to show that this is equal to this. Now that's actually fairly easy in fact. We're taking x here as a real number, n's non-negative integer, and we're doing the integral dz. So this is really just using Cauchy integral formula in the generalized form, and that's easy to show. Now, assuming the validity of term-by-term integration, then you're asked to show that this sum, so summing both sides, the sum of n equals 0 to infinity of x to the n on n factorial squared, can be written in terms of this contour integral. And now you simply take c to be, so c here is any contour containing the origin. So I should have said here, C is a closed contour containing 0. And if you now take C to be the unit circle centered at the origin, then you can find an expression for this infinite sum in terms of a nice real integral. So there's a nice little challenge problem to play around with there. Well, we have a look at some of the further implications of the Cauchy integral formula and the generalized version. It's got quite a few, in fact. So firstly, if we take an epsilon neighbourhood of the point z0 and we set C to be this circle, centre z0, radius epsilon. Now if f is analytic at z0, then it's differentiable at all points in that neighbourhood for sufficiently small epsilon. Now, using the Cauchy integral formula, the generalized version with n equals 2, we can write down this expression for the second derivative. And we can see from that then that f double dashed is also defined at z0. So if f is analytic at z0, then f double dashed is defined at z0. And at all points in that neighbourhood, and the we simply perturb z0 slightly within the open disk. You can now give an inductive proof of the following, that if f is analytic at a point, then its derivatives of all orders, f dashed and so on, are also analytic at that point. Now that's not true in the real world. You can find plenty of functions that are differentiable at a point, but the higher derivatives are not necessarily differentiable. So this is a result which is only true for this word analytic. So analytic is much more powerful than differentiable, in fact. Analytic's not a concept that we have in the real world. So the following result, it gives a sort of converse to Cauchy's theorem, a sort of perhaps partial converse. So we have, if f is continuous throughout a simply connected domain D, and for every, that's the important point, for every closed contour C interior to D, we know that this is true, then we can conclude that f is analytic. So, of course, Cauchy's theorem is the other way around. If f is analytic, then we know this is true. This one says if this is true for every closed contour, then f has to be analytic. Now, I'm not going to prove this result. Again, you'll find this is called Morera's theorem. You'll find this on the web or in books. The following result, however, is really quite stunning. It was actually due to Koshi, despite the fact that it's called Liouville's theorem. And what it says is that if you've got an entire function, that is one which is differentiable everywhere, and you're told that it's bounded, well then immediately I tell you it can't be very interesting. It has to be just a constant. That is, there are no bounded entire functions in the complex plane. Which, if you think about that for a minute, that helps to explain, for example, why the complex sign in modulus was no longer bounded. If it had have been bounded, then it would have had to have been a constant, but of course it's not. So, by bounded we mean that there is a real number m, so that the modulus of f of z is less or equal to m for all complex numbers z. Okay, the proof of this is quite nice. It's not very hard. So suppose f is an entire function. Take an arbitrary but fixed point z0 in the complex plane, and suppose capital R is a real number bigger than 0. Now we're going to then apply the generalized Cauchy integral formula for n equals, well, it's actually really n equals 1, isn't it? Not 2, if you put it into the formula. So generalized Cauchy integral formula for n equals 1, and we get this. The first derivative is given by that, where I'm going to take this gamma to be the circle centre z0 radius capital R. Now we're going to apply the ML estimation lemma now and take the modulus of both sides. So the modulus of 1 on 2 pi I is 1 on 2 pi, and then we want the maximum of the integrand, which is this, and times the length of the contour, which is 2 pi r. Okay, so that's what we're going to do there, and then we now let r go to infinity, and then we can say this is now less than, this is the maximum, over r. We now let r go to infinity, then that means the f dashed of z is going to 0, because this quantity here is going to 0. So f dashed of z goes to 0. Now this f of z was arbitrary, and so that means the derivative of every point in the complex number, in the complex plane, is 0, and that means it's a constant. And that's the end of the proof. Well, little challenge problem, which is a very nice one to do, uses exactly the same idea as we did above. We suppose f is entire, and that there is an m, which is real, so that the nth derivative at z in modulus is less than this m times the modulus of z to the n. That is, the modulus of the nth derivative is bounded by some constant times the modulus of this polynomial z to the n for all z in C. Then f is a polynomial of degree at most n. So this is roughly saying if you've got an entire function whose nth derivative is essentially bounded by a polynomial of degree at most n, then that function itself must be a polynomial degree at most n. Using Liouville, we can finally give, well, reasonably rigorous proof of the fundamental theorem of algebra, and of course that one that you know from earlier courses in mathematics, that a polynomial p of degree n bigger or equal to 1 has at least one 0 in the complex plane. And here's a little proof of that. So there's my polynomial, and the an is not 0. Now, for contradiction, suppose that this is not 0 for any complex number. So suppose this doesn't have any roots in the complex plane. We're going to define q of z to be 1 over that, and that's going to be an entire function, because this p of z has no zeros. So the denominator is never 0, so this is going to define an entire function, analytic everywhere. Now, if z is not naught, then this q of z, we just write down what it was, and I'm going to divide top and bottom by z to the n, which gives me this expression. Now the point is then, as mod z goes to infinity, this thing here, the top is going to 0, all of these terms are going to 0, but we have an an here which is not 0, so we get 0 over an, and that's going to 0 as mod z goes to infinity. So that means there is some radius r, such that eventually, if this is going to 0, then mod q of z is less or equal to 1 whenever mod z is bigger than r. But this q is continuous on the closed and bounded disk centered the origin radius r, and hence that means it's bounded on that disk. So q is an entire function that is bounded, and so it's this first bit showed that it was bounded whenever mod z is bigger than r, and it's also bounded whenever mod z is less than r, and hence it's bounded everywhere. So it's a bounded entire function, and by Liouville's theorem it must be a constant. Well, if q is a constant, then p equals 1 over q is a constant also, and that's our contradiction. And that is the end of section 7.